function which is periodical. And here it is expressed by the complex exponential, which is a cosine and a sinus. It can be expressed by the sum of sinusoidal functions, each periodic function. If you have just one single frequency, here one single frequency, the Fourier representation gives us a spectrum. Spectrum means it shows which frequency with which amplitude is present in our signal mixture. And if you have a single frequency, of course you get a single peak. If you have several frequencies, and they are even corrupted by noise, then you see here even more noise, less noise. So you make this analysis. It worked later. It worked later. So if you just work out, got connected. Then you see the spectrum here, and it shows me, okay, there are a lot of frequencies which are related to the noise. And here we have 3 peaks, and that means we have 3 main frequencies, and they are shown in the spectrum. If we enhance our measurement time, so the longer I measure, the better the results are. And you see here a longer measurement. Here we have 10 seconds, here we have 100 seconds. And then the same spectrum, but it is clearer. You see it's finer, more distinct, these peaks. And you see also the noise is further reduced. Because it makes an, I could say more or less an average over it by doing the spectrum analysis. Okay, that's this one with a sinusoidal. Here we have now another periodic signal, which is a rectangular pulse train, we call it. Rectangular pulse train means it is periodic, with a periodicity of t0, and the pulse has a duration of tau. And if we make now this calculation, now the formula to calculate is very, very simple. And it gives me a sinus x over x. That is such a function. We have seen that yesterday. And now I can just add up 1 sinus x over x, 2 sinus x over x, and so on. Remember, there is here this sum here. The ck's are the sinus x over x functions. And we have to sum them up with different frequencies. And if we do that, you see, we have here only 1 sinus x over x. Here you overlay 4 sinus x over x with the different higher frequencies. And you see already it looks a little bit like a rectangular shaped pulse. If you have 100 or 1,000, it gets even better. So the more I overlay, the better it is. And you remember here, Fourier stated you need infinite numbers of those sinus x over x, so an infinite number of overlays. In practical use, this is not possible. We always have a finite number, and remember we saw yesterday when you put here 10,000, that was nearly an exact rectangular pulse train. That is fair enough. Of course, if you dive in and make a big zooming in, you see still some deficits. Yeah, it's not a complete 90-degree angle, but as I said, Fourier stated you need even more. What has that for a practical impact? The practical impact is that you have here, for example, a DC voltage, and you switch it on. And this switching on of a DC voltage is like a rectangular pulse. And that means, if we look at our Fourier series representation, that such a pulse creates, or such a step function, that such a step function creates a lot of high frequency components in the end, which influences the electronics around it. So that is this one here. what we see if we look at our spectrum, and that is now M25. M25, we plot the amplitude and the phase of this sinus x over x spectrum. Yeah? And I do this here for a special duration, that is this tau, and we have a periodic time or a periodic frequency which is 1 over T0 and T0 is 20, just for some given values. And then you see I have this sinus x over x, the ck's, I do compute them. You see here, from minus T0 to plus T0, this is my sinus x over x function, and then I plot that, the phase and the amplitude. So the amplitude of these ck's and the phase of these ck's. You see here, where is it? Here is an absolute value of my ck. And the ck is this value here, which I compute, and I compute these different ck's for minus T0 until plus T0. Okay, so if I run that, you see I have here the amplitude spectrum of a periodic pulse train ck. And what does that mean? This is a periodic pulse train which we have seen. The ck, we saw that before. Remember, here, the ck's just overlaid, summed up. We sum them up, and then we get this pulse train. And if we look at these, the spectrum of each of these coefficients, and then we see some peculiarities. The ck is that function. K is something which changes from minus to 20, for example. And what we see is that we have here single amplitudes. These are the values of my ck, the absolute values that are the amplitudes. You see here, these are the amplitudes. Here we have, for example, the C0. Here we have the C2. You see x, that is k is 2. There we have the C5. You see this sinus x over x. You see that very nicely here. And the longer or the bigger the k is, the less amplitude we have. And here we have the phase. Sometimes it is positive phase plus 180, which means a negative value. The sinus or the sinus or x over x for p is minus 1, and the sinus x over x for 0 is 1. We have seen that already yesterday. So we have here plus and minus. Here's the absolute value. And the story about that is that here we have, because of a periodic frequency, a periodic signal, and because of the Fourier transform, we have single amplitudes in the spectrum. It is a discrete spectrum. You see, here are the amplitudes. In between here, there's nothing. So we have single amplitudes. This is a discrete spectrum. And that is the story behind that. So periodic, I write this down as a statement. Periodic signals do have a discrete spectrum. And this discrete spectrum is K 1, 2, 3, 4, and so on, and there's a 0, and that is my CK. You see, you have here some values, whatever it is. For example, the absolute value or the phase. Yeah? This is discrete, these are as a discrete spectrum. And that reflects the CKs. Yeah? Each CK is one component at a frequency K times omega 0, the base frequency. And here our base frequency was 1 over T0, the duration or the time between one pulse and the second pulse. Now you see that here, wait a minute. You see here we have T is 0, here is T equal capital T0, so that is the pulse duration, the pulse periodicity, and the pulse duration is tau. Yeah? And you see our delta Fs here between these peaks here, that is equivalent to the periodic time of my base frequency. And the base frequency, this T0, is the periodic time of the periodic signal. So if you have, for example, such a signal, here I make an example. We have a signal here, and we have a signal here. So this is here my T0. Now, if you have something else later, you will have a signal which might look like this here. So you see between here and here, you have also the T0. So the periodicity with a frequency F0, that's the periodicity, is 1 over T0, and our delta F, the delta F in the spectrum, that is 1 over T0, and that is F0. You see that here. And you see this here in my spectrum. So that's what we learn. Periodic signals do have a discrete spectrum, that is the kernel of these graphs. Now I show you another periodic signal just for the sake to have a second one. This is this sawtooth type signal, Sägezahn. A saw ist eine Säge, Tooth ist ein Zahn, Tooth, Sägezahn, a sawtooth signal, looks like a saw. Yeah? And here again we have a periodicity with T, capital T, and then we have here a very simple signal, it's just a line, and you can define such a signal like this. F of t is 2 divided by t times t, between minus and plus t half. Don't bother about the negative times here. The negative times just are a question of mathematics. They are not real physical times. This is the mathematical representation. We can always shift a signal here to a positive time by shifting it to the right. And if we do this, we can compute the A case and the B case. I don't derive that. You can look that in the other script if you really want. These are the A case and the B case. Where? Here? No. Here. The C case are that A case plus J B K, and the A K here in this special case, oh wait a minute, just a second, that snapshot, that is 0. So we look now at this fourth, I copy it, maybe I just get it in here. These are our CKs, and now we are looking at this sawtooth type signal. I copy this, is better than drawing it. You see, this is the signal. And I don't dive into the calculation in detail. I just give you the final signal or the final result, doing some calculations with the C case and the B case. You see, you get a sinus omega 0, you get a sinus 2 omega 0, you get a sinus 3 omega 0, and what you see also that these amplitudes are diluting to 0, 1 over, let me see, here you see that, where is it, here, these BKs, yeah, maybe I put that also in here, but I don't want to dive into this, to derive that. You see, the amplitudes of the spectrum tend to 0 with increasing frequency. Tend to 0 with increasing frequency, 1 over k. Yeah? This is the BK, and you see that here 3, 2, 1, and you see this is going to smaller values. So the AK is 0, you see here, AK is 0, and the BKs, they are plus or minus 1. And then we have here the sinus, you see that is the function. I can do that here this way, just plot it underneath or print it underneath. So you see the AK is 0 here, so that is 0. That is 0. Then you are left with this signal, and the real signal then gives me this sinus signals, and here I use just not the complex one. The complex signal can always convert it to a real signal by adding its conjugated complex to it. Here that's just the math. Math just gives me the complex part, but in the real world we have, of course, the real part of this complex amplitude, or we have the amplitude. So that's the spectrum here. You see plus, minus, and I would like you to see onto 27. What is 26, by the way? Let me just run that. I'm not sure what that gives me. Okay, that's a different story. I left that out. Yeah. Okay. So no, I want this here. And you see now I go with, let's start again with 1 base frequency, And you see, you get something like this here. That's the sinus. F0 is 1. So 1 frequency, nothing special. K is 1. Then I go for K, let us see 3 for example. So I overlay now 3 sinuses according to the function. Oh no, that is, what did I do? I changed the wrong number. F0 is 1, yes. I had to change this one here. So that was now 3, for example. See, you get 3 sinuses combined. 3 sinuses combined, 3 frequencies overlaid. So according to this sum. Yeah? So let me just get this a little bit together. This is my sum here, you see? That is my sum. This is my sinus. This is the reproduced signal out of a sum. And now I have used only this part. So this part here, not that here, but this part is that. That is 3 frequencies, only 3. And now I'm going to 30 frequencies, yes, to show you what that means, 30 frequencies. And now you see that looks much better already. So I have overlaid now 30 frequencies. So that would mean, for example, here f of t is roughly 2 over p, so sinus omega 0 t minus 1/2 sinus over 2 omega 0 t plus and minus plus minus sinus 1 over 30 sinus of 30 times omega 0 times t. Yeah, so you add up now 30 values, 30 frequencies. And you see slowly it overlays. Yeah, this is the Fourier presentation. And if I exaggerate or if I increase this for, let's say, 3,000 or 2,000 or 5,000, whatever you want, just a big number. I saw here 3,000 is fair enough. And then you see here, if we zoom in, it's not a complete rectangular pulse here, but it's fair enough. You see, there's still some rounding. But if you look in total onto this picture, you find that's a perfect sawtooth shape of a signal. So this is 3,000. So this K goes from 1 to 3,000. 3,000 frequencies or components, frequencies are overlaid. It starts with my overlaid. Okay? So that is the story behind that. Any periodic signal can be produced. Here you see this overlay. That's the base frequency. Then comes 2 frequencies. Maybe we just run it here. 28. But as I said, you have all these files. Try them out at home. Yeah, try them out. Or if you do it now here with your computer, try it. It's very impressive. You can always change it here, for example. I have 10 harmonics, as we call them, build the final signal. So you see when you run that in the end, these are overlaid, and you see already, I print here all these CKs, all these components, the sinus, K times omega 0, 1 over K. I print them, the single one, you see, and then when you add them all up, it comes to, let us say, we put here, for example, 1,000, for example, then you see the picture is not nice anymore because it has to take some time also. Maybe it's too long. Maybe it's too long. Now here. You see, it takes some time. I didn't have here the rest. The legend is in the end useless. You see, the overlay gives you this browny composed signal. What is the matter? I wanted to copy this. He's still trying to copy. That's a huge number of values. That is wrong. Let me see whether I can make this a little bit smaller. I can copy this. Here we are. So it takes some time to get all the data processed. Overlay of 1,000 sinus components. Yeah, so you have a sinus of omega 0, and you have a sinus of 1,000 times omega 0 t. Now these are the spectral components. These are the sinus spectral components. These are the spectral components. And as I said, the spectrum here, that is the spectrum. Let me see here. That's the same thing. That I don't have a file for the spectrum, I guess. I'm not sure. No, I don't have a file for the spectrum. But that doesn't matter. We can imagine that this spectrum will look like, you see, look like this here. We have here a signal, and we have here another signal, and we have here a signal, here a signal, there a signal, here a signal, there a signal, here a signal, and that goes along with omega is k times omega 0. And this is k is 1, k is 2, k is 3, and so on. And this is the spectrum of my sinus 1 over k plus or minus 1 over k sinus of k times omega 0. And you see that goes down. That's in the end this spectrum here. Here, that is this spectrum here. I should have printed this directly instead of painting it, because that is a much nicer print. Okay, why do I use all that stuff? Why do I use this reconfiguration of a periodic signal? That is the question. So for the sake to have that is very nice. You see, okay, I understand that if you overlay, you can reproduce or reconstruct a signal, a periodic signal, very nice. But what is the reason behind that? Why do we do that? And the reason is this here. The reason is this here. So imagine you have a signal which is unknown, that is transmitted. You receive a signal, and this signal will contain some information, but you do not know which information, so you have to detect or to analyze the system. But the signal, because of the transmission, is distorted, it's disturbed, there is noise on it. And maybe some other frequencies. As I said, if you switch on a motor, because of this step input, there are a lot of high frequency components radiated and broadcast into the environment. And that is a disturbing signal, of course. So what you get is something like this. And therefore, the first thing you do, we make an FFT analysis. So we look at the spectrum, as we did before. And with this signal here, for example, we get something like that. Now we see, okay, there is a spectrum here. There is one huge amplitude. There is a lot of noise, and there's another huge amplitude. So we know that. And because of this knowledge, we see, okay, the noise is a component which I don't want. That's a component which is an offset, a distortion of the signal. I don't want that. So I want this amplitude or this frequency and this frequency. And what do? Now comes the next step, and we make a synthesis of the signal because of the Fourier representation. And we have here, we call this a filter bank. And the filter bank contains these CKs. And with this and the Fourier representation that our signal is a sum of the sinuses and cosines, so these complex exponentials times the CK. And then we get our reconstructed signal. So from here, we call this a synthesis, we call this an analysis. Here the Fourier analysis, so measurement, analysis, and then the synthesis. The synthesis with the coefficients, which I find here in my spectrum. And then I synthetically produce a signal, therefore we call that S with this roof on top, that is a estimation, a digital estimation, therefore S of n, discrete values, we will see that later in the day, of the real signal S of t. S of t is the real signal, and S of n is then the reproduced or the estimated because of here our analysis and the reconstruction through these filter banks. So, as a summary of all that, we know periodic signals with a periodicity time of T0 have a discrete line-shaped spectrum at discrete frequencies k times f0 or k divided by T0. So the frequency resolution depends on this T0. Now that is the resolution we have. So there is no other value in between. So for example, I have here a frequency, there's a frequency, there's a frequency, in between is nothing. So the spectrum has discrete values and it is line-shaped, linienförmig. Linienförmig means the shape of a line. die Form einer Linie. Linienförmig, that's the adjective. The frequency resolution, Frequenzauflösung, depends or is increased with the number of these parts which are summed up, with K. The overlay of these different components, these spectra, do give us a periodically, the periodic signal, the reconstruction of the periodic signal, and that is the base for a signal synthesis. That is, in the end, we reproduce the tooth-saw signal, which may come in and has a completely destroyed shape, and we know, okay, this is a tooth-saw signal with the different frequencies, and these frequencies we sum up with the CKs, which come from the analysis, from the spectrum, we sum them up and we get them reconstructed. Okay, so far so good. That is periodic, the periodic signal synthesis. Of course, we do not have periodic signals always. Remember the step, remember the pulse, remember a exponential function. They are not periodic, they are continuous. And now we convert or we look at the representation in the continuous time for aperiodic signals. And the series, we see that here is series, which is a sum, that converts, if T0 now, in our imagination, that is the periodicity time. If this T0 goes to infinity, the periodicity disappears. If the periodicity time is T0, that means every signal is periodic with T0, and this T0 goes to infinity, the periodicity is eliminated. You see here, that is this T0. If that goes to infinity, I'm left with a rectangle pulse, for example, here alone. That's the single signal, which is now aperiodic. And if we do that, you see the CKs here, and that is the integral over K, over T0. Here is 1 over T0. Yeah, that converts now into a transformation, into a Fourier transformation, a Fourier transform. So the Fourier series, here you see the sum, that is now an integral. The discrete sum goes to an integral. And this sum here is represented now by the Fourier transform. And the Fourier transform, again, like in Laplace, it has is indicated with capital letters. Now, if we have, for example, here an x of t, and the CKs are our components in case of a periodic signal, that converges into a capital E x, and that is now the Fourier transformation. And you see this 1 over T0 that goes more or less to 0, and this K omega 0 that goes to, here I said 2pf. F is now a continuous frequency, because here the delta f, which we had in the periodic case, that was 1 over T0. If delta f goes to 0, we do have not a discrete spectrum, they have a continuous spectrum. And you see that was here, let me make that a little bit bigger. You see that was in the periodic case, the frequency resolution, 1 over T0. So T0 goes to infinity, that means this gap goes to 0, and instead of having a That was not good. No, that was not good. Instead of having a discrete spectrum, you see we have a continuous spectrum. And in case of this rectangular pulse, I have a sinus x over x spectrum. It's not discrete anymore, it is continuous. That means any non-periodic signal contains any possible frequency. Any possible frequency, not discrete ones, any frequency. And that is the story about that. Here I just gave you a foil which makes the relation between the Fourier transformation and the Laplace transformation. Laplace was also a transformation for any general signal. Now we had step, we had sinus, we had a delta impulse. You find in tables, you find any signal you want. Exponential functions and so on. And here that was our Laplace transform, and if we just put S equal J omega, which we did already in the Bode diagram, then we have here our Fourier transformation. It's exactly the same formula. Instead of S, we have J omega. Therefore, I said at the very beginning when we introduced this Laplace transform, if you look at the y-axis, so S equal J omega, that is the Fourier transform. So if you look here, for example, into our spectrum or into our transformation variable S, and that is the area of S, that is J omega, and that is sigma, and S was sigma plus J omega, so a real part and an imaginary part. And if we look just at this value here, well, let me put it that way. Here we have S equal J omega, and that corresponds to the Fourier transform. F, now that's not nice. Let me see, that is the F transform. The F transformation. It's so curious when I'm home in the hotel and I use this rubber, which is the back here of this pen, and it works fine. I can always switch to the pen itself without any problems. Here I have this problem with these funny sidelines. So that is the Fourier transform. So the Fourier transform is a special case of the Laplace transform. So if we look at a special signal, the step, we have seen that, the step impulse here, no, that's a rectangular pulse, not a step, excuse me, that's a rectangular pulse, a simple one, rectangular pulse. So this pulse looks like, again, we have a negative time, just for the sake of mathematics. We go here from tau half minus tau half to plus tau half, and you get this pulse here. It has an amplitude of A. This is our x of t. This is t. And if you get this simple formula in here, you see x of t, that is very simple to calculate, because now I have only for my transformation, which generally goes from minus infinity to plus infinity over t, but the signal does exist only between plus and minus tau half. So you see it's very simple, and that is an A, the amplitude, a constant value, and the integral of the exponential, that is very easy. That's 1 over minus j2pf, and then you can combine this plus and minus the, this is a complex number, and complex and conjugated complex, you combine that together, and then you find that this is a sinus x over x again. Yeah. A tau sinc of p f tau. Sinus x over x compared with this tau. Tau here is the parameter of my signal, the duration of the signal. A is the amplitude of the signal, and f is now, you see, that's the continuous frequency. And the higher the frequencies, that is now very nice. If you look at this here, you get this result. Yeah, that is the result here, and that is the sinus x over x. That is the sinus x over x, and we have seen this sinus x over x already, and that goes from here and that goes for f going to infinity, the sinus p f tau divided by p f tau goes to 0. So what we see that it contains, this pulse contains all the frequency, theoretically, all the frequencies, theoretically, but the amplitude goes also to 0. So that would mean from a certain frequency onwards, the amplitudes are meaningless. And that depends on the tau, for example, here, what tau we have. If tau is very small, then the higher frequencies are present, because then p f tau remains small. If tau is very big, then the smaller frequencies, or the limit where the amplitudes are important, are going to smaller frequencies. So you see, theoretically, yes, all the frequencies, but in real practical applications, we do not have to regard or to look at all the frequencies. Theoretical, the aperiodic signal contains all frequencies from f equals 0 to infinity, but the corresponding amplitudes go to 0 with increasing frequency. And that means actually two things. You do not have to look at all the frequencies. Some are from a certain point on, they are unimportant, they are just too small. That's one thing. And what was the second thing I wanted to say? No, forgot it. Two things. The frequency are not important. That I don't know what the second point was. So we have to look only at a limited frequency band. So that means only what's here now? only a limited, what is that? Look at this here, this is horrible. I don't touch the screen and he's still printing. This is somehow...
Ghosting.
I've not found out what the reason for that is, where I can discharge this electrical effect. Only a limited frequency band is important. Technically important. So I do not have to look at all the spectrum. So in the end, that means also practically the frequency, the spectrum is limited. So then you have, for example, here your x of omega, the amplitude, yeah, and then you have something like this here. And from here on, yeah, the amplitudes are so small that we can neglect the respective frequency components. Okay, that's the practical background. So everything is somehow limited. Electrosmog, that's what I told you when you switch on a motor. We call this smog because this is disturbance, this noise, electrosmog. Actually, if you would be able to see all the frequencies which are present in this room here, nobody would see the neighbor next side. If you could visualize that with a color. The ambient air is completely full of frequencies, either with the smartphone, with lamps, with projectors, with electronic, whatever we have. And if they are powerful enough, for example, if you switch on a motor, as we have seen the amplitudes can be important or big enough to disturb electronics at the side. Another one is the exponential function, a decaying exponential. And if you make this transformation, you can also easily integrate this integral. Sometimes the integral is very difficult. And again, as I said, we have tables where these Fourier transforms are accessible. We don't have to do the calculation manually. And you see here, we get for this exponential, you get this value, and if you look, that is exactly what we had. J omega equal S. J omega equal S. You see, sometimes I use the capital omega here. I was a little bit reluctant. I was using, where was it here? I was using, where was it here? Frequency omega 0 here. Don't worry too much about this naming. omega or omega 0 in the time continuous domain is more or less the same. We will come today, we'll come to the discrete representation, and then it makes a difference because the small letters indicate, they do indicate normalized values, but we'll come to that later in the day. Okay, this is another one. And the summary of all that the spectrum of an aperiodic signal is now not discrete anymore, it is continuous. All frequencies are present, but the amplitudes are also reduced the higher the frequencies are. And the reason for that is very simple, because any amplitude in the frequency, here they contain in the end the energy of the signal. Now, if you make a integral over that, this is the energy of the signal. Signal energy content. And any signal must be in its energy limited, otherwise you would explode or you would destroy your equipment. If you would here radiate a signal with an unlimited energy, it's like an atom bomb. You would destroy everything. So in real technical cases, the energy of any signal is limited, and that means higher frequencies are present, but with a very, very low amplitude. So the contribution of the high frequencies to the energy content is also limited. Energy of real signals are limited, and that means the energy contribution of the high frequencies, of the higher frequencies, are limited. And tend to go to zero. That is the facet and the summary here. I can add this here also. Present, but with decreasing amplitude. I should actually add this in the foil, mit verschwindender Amplitude. Let me see, I just add this. That should actually be part of this statement. I do it right now. Aber mit verschwindender Amplitude. So. Aber mit verschwindender Amplitude. Ja. So that is actually the the issue behind that. Here I have given you a list. I do not want to derive that, to present that all, but here is the step. You see that it's just this one, this decaying one. We have a decaying exponential. That's the 1 over we have seen. These are the two which I presented. Here is a sinus. You see a sinus, continuous sinus. We have frequencies. Actually, we have plus and minus frequencies. Yeah? But for the real technical application, we have only a causal signal, and that means the causal signal is not non-periodic anymore, because periodicity means from minus to plus infinity. And what that means is that this real peak is now diluted into a peak with, you see, with this signal here. It's an overlay or multiplication of this causal signal, the step, and the sinus. And if you look at this decaying value and this peak, you see you get this peak, but at this value, omega 0, but it's also decaying. No? It's not a single peak. So we see that these spectra do interact as well. If we look at the multiplication of the signals, you will see that in a minute. Here you have some other examples. Cosine and the cosine or the sinus are decaying. You see here also you get this amplitude, the maximum at a certain frequency, omega 0, and then it decays. Here is the phase, and there is the amplitude. And there is something very astonishing, actually. There is a cross relationship between time and frequency. So if you have a time signal, it has a certain spectrum. If you look at this spectrum as a single time signal, as this here is a sinus x over x, remember that is the amplitude only, yeah? So it's the absolute value. So if we look at the spectrum, that's a sinus x over x, as we have seen. If we put this sinus x over x as a time signal, we get the spectrum of the corresponding signal. Yeah? So there's a cross relationship. Rectangular pulse gives a sinus x over x spectrum. The sinus x over x signal gives a rectangular spectrum. That's quite amazing, and sometimes we use this relationship to find new spectral presentations. Here, same. A constant value gives me a constant value in frequency spectrum. This constant value has for all times the same amplitude. So if you would integrate this signal, that would have an infinite energy, and all the frequencies are present, theoretically. And if you put here a pulse, gives me a pulse in the spectrum. So this here gives me a pulse in the spectrum. The constant value gives me a pulse in the spectrum, and the pulse in the time gives me a constant spectrum. This pulse is theoretical again. It has infinite amplitude and a duration which goes to 0. So the integral over this one. Okay. There's another issue. I do not derive that. It's easy to derive, but if you look at this here, we call this a frequency comb or a time comb. Yeah? This is a time series of pulses, and if we look at our frequency or our definition of the definition of the Fourier series, yeah? You see, this is just an impulse, and the impulse, if we would enter this into this signal, that x of t would expel only at these discrete values a value for the spectrum. The integral over delta times something, now the integral over delta of t0 or t, let's put t minus t0, for example, times f of t dt, that is f of t0. Now, using this relationship, yeah, because this delta pulse just expels, draws the function only this single value out, because it has only here an existence, and we get, for that, we get here this relation. Pulse comb gives me a frequency comb. They are the same. Pulse comb in time gives a frequency comb in the spectrum. Now also only single frequencies, and so on here is the time signal, time pulses. That's a peculiarity of pulse combs. And there's another thing which we have to look at, that's the multiplication of two signals. Remember, you have a modulation. In in communication theory, you modulate a signal. For example, a DC on an AC. Because the AC can be transmitted easily, and the DC is the amplitude, is the signal content. So you multiply the signals in the time relation, or in the time in the time domain. You have here a signal S1 of t, which is aperiodic, and then you have an S2 of t that is periodic. This is aperiodic, and then you multiply them, and now you get a modulation of the S1 over S2. You make a modulation. And the spectrum here, you see that is S1 has a continuous spectrum of omega is continuous, and the S2 of omega is discrete. And what we have here, you see that is the transfer, the Fourier transformation. That is the signal S1, and that's the signal S2. And you see there is a ck, there is a sum, and because of the fact that these are linear operations in math, I can put the summation in front of the integral, and then you see here there is an f0 kt, here is an ft, f times t, and then I put these exponentials together. Yeah? E to the power of x1 times e to the power of x2 is e to the power of x1 plus x2. So we sum them up here. And if you look now into this x, this was my S1, that is my S2 of t, and that is the spectrum S multiplied of omega or f, of f or omega. F is equal to, is a little bit, I should make that equal. F is equal to capital F, omega is equal to capital omega. I don't care about the capital ones. So you see, we can get this out here because this is a linear operation. I can interchange the sum and the integral, and that here, you see, that is now the same x is the aperiodic one, that is the aperiodic Fourier transform, at a f minus k times f0 frequency. It's just shifted. And that means, that is very important. You see, the spectrum of the multiplied signal or the modulated signal. The spectrum of the modulated signal is the spectrum of the aperiodic signal shifted to the modulation frequency and the multiples of the modulation frequency. And that has a meaning. If you look, for example, into this scenario, given is an aperiodic signal. The aperiodic signal. This is the periodic signal. And you have a discrete spectrum. These are the CKs. This here is a continuous spectrum. It contains some frequencies which are important until a max frequency B. That's the max frequency. Which is important. Is important, or which is notable. The rest, the amplitudes are going to zero. that is just for the sake to make it graphically easy. So you have a spectrum here, and then you have spectra here, 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 and so on. And now comes the modulation. We get this aperiodic spectrum now here. Now let me just do this in red. We have this here, the spectrum. And then we have the same spectrum multiplied with a C1 or a C0. No, it's a C1, excuse me, this is C1, because here we have 1 times F0 or omega 0. Depends on your axis. So it's shifted, the same spectrum is shifted to the base frequency of your modulation, of the multiples for the aperiodic signal. And it has a reduced amplitude. Then you get another one, you want it or not, you get another one here, even a lower frequency, a lower amplitude at a frequency of 2 times F0. Yeah. And what does that mean now? I will just expel this here for a moment. Yeah. So the modulation, the signal multiplication which is a modulation, signal multiplication periodic plus aperiodic, yeah? That was the case which we had looked at. And that is the modulation. And this modulation shifts our base spectrum, which could be on low frequencies or could be in a special frequency band. That shifts it to a higher frequency band here. And what I could do now, I could put here a band pass on it. And just expel from the transmitted signal only this frequency band. And that is the reason of modulation. Yeah? So you transmit a signal in a higher frequency band, and once it's transmitted, because you have some channels when you make a transmission of news, any transmitter has a certain channel where he is allowed to transmit signals. So he makes the modulation. That means he is shifting his information, which is the aperiodic signal, shifting his information into a frequency band which he is allowed to transmit. That is my modulation frequency. And then he transmits the signal, and when he receives the person who wants to receive the signal, the receiver, then just says, okay, that is my frequency band, and I filter with a band filter my information back to the original frequency range of the aperiodic signal with a band pass. And the higher, you see, the higher components have less amplitude. Yeah? There are some here indicated. They are less amplitude. They are diluting to 0 the higher the frequencies are. So these multiples, as we say, of the modulation frequencies, the multiples and the multiple spectra, they are not so important anymore because they are in their amplitude, they are reduced. And that is the reason why we have this modulation. So we transmit the information. That is my S1, aperiodic, is lifted by the modulation into a specific or let's say allowed into a specifically allowed frequency band. That's this one here. That's this one here. And at the receiver end, will be reconstructed or will be expelled by a bandpass. And then we get back our original frequency, or our original spectrum. Okay, and then of course with this spectrum you can make an analysis, an FFT analysis, and then you make a synthesis of your signal. But that's the reason why this multiplication is so important. Yeah? So you multiply Multiplikation eines aperiodischen mit einem periodischen Signal. Die Frequenzbereiche bedeuten eine multiplikative Überlagerung der jeweiligen Spektren. A multiplicative overlay of the respective spectra. The spectrum of the aperiodic signal will be periodically repeated at the multiples of the base frequency of the periodic signal. In the time domain, this means a multiplication, and that is an amplitude modulation. That is the translation of this German text. But you can read this German text, right? Can you?
Yes.
No?
Yes.
So if not, I mean, I've intentionally left the foils in German. I initially wanted to translate them, but I did not do it because you have to learn anyhow German, and that's a very good exercise. Yeah? You learn also the specific idiomatic expressions like Überlagerung, multiplikativ, periodisch, Spektrum, Amplitudenmodulation, and so on. But if not, just copy and paste into a Google translator, and then you see the English or the Malaysian translation. I've made here an experiment to show you this. Yeah, that is 29.1. I added this here 29.1. What I do here is demo a spectrum of a sinus wave. Or let's say that is not really the spectrum of a sinus wave. It is the spectrum of a sinus wave multiplied with a step function. With a step function. You see, here's the sinus x over x. That is my aperiodic cycle. It's not the aperiodic, it's not a step function with a exponential function. Exponential function. We have a break now. Yeah, I know. Let me just finish that. You see, that's the sinus, the periodic signal. That's the aperiodic signal. And then we do an FFT analysis. That's the spectrum calculation. FFT, we will see that later next week. FFT is the, if you look at F1, in the help center, it says fast Fourier transformation. And you see there are some examples, more or less what I showed you also. Yeah. By the way, if you look at the help function, you can easily, easily expel that. Let me see, I need all of that, of course. But what I wanted to show you, if you just copy this, Control C to the clipboard, and then you go into the work, for example, copy C, and I go here to my MATLAB, Control V, and you get everything defined. So you can use these examples in the help file. You can use them line by line. You can compose them to an M file, and you can easily then run this here. Sometimes you see here open live script. Yeah? That opens directly in MATLAB, this live script, and then you can jump from one section to the other section, run it to this section, run it to this section, run it. Yeah? And then it plots, for example, here, here, that's the signal. Actually, you should run that. It doesn't do that. Let me try to run the whole thing. Strange, why doesn't it do that? Why does he not do that? Here, we run. Then we run this one here. Okay, run it. Then we run this here, run it. But I want the plot here. I don't get the plot label. Strange. Let me just get this again. Run. Strange. It does not plot that. Run. You see, he runs the section. I don't understand that at the moment. Should run the whole thing. Run it completely. Noisy signal. Run the whole thing. But it doesn't do it. I don't understand why. Normally it runs the whole thing. Very strange. Maybe during the break I have to look at it. So we do this FFT, as I said, FFT, fast Fourier transformation. This FFT gives me then the Fourier transform, and when I do that, here in my, where is it, 29 underscore 1. So this is something very strange, I don't understand. 29 underscore 1, that's this here. You see, I have my FFT, and then I plot this, and I plot the absolute value, which is the spectrum, and I plot also the, where is it here? I plot also the, no I didn't, the phi. Actually, you can plot the phi as well, the phase, but I didn't do that. I just plotted the absolute value. The combined signal and the periodic signal and the aperiodic signal. And we will do that all together. And you see, we have here subplots. I got them all together, 3, 2, 4, and so on. a little bit more. You see that is my periodic signal. That is the spectrum of the periodic signal. Then I have this exponential, the aperiodic signal. This is the spectrum of the aperiodic signal. And then I combine this one times this, which gives me a sinus which is decaying here aperiodically. And you see now this spectrum, the aperiodic spectrum, is shifted to this frequency. That is the base frequency at around 6 here. You see 6, and that is shifted here also to around. Give me the values. It's strange, he does not repeat them. Here we are. See, it's a little bit diluted. 5.9, 6.00, there it is. You see, that's corresponding. And this amplitude here at the very beginning, you see, that is my decaying. Amplitudes are not important here in the moment because it's not an ideal one-to-one Fourier transform. It is a fast Fourier transform, and that takes into account that there are adjacent values, and these adjacent values would sum up to the amplitude here, in this case of 34. Okay? 15 minutes until 10 to 11. Okay?
Okay.